folks. In this video, we're going to talk about the first topic of Chapter 9, energy. We'll talk about the common units for energy, and then we'll discuss the first law of thermodynamics, and then introduce internal energy. This topic is mainly about important concepts regarding energy. Let's take a look at the units of energy. Well, two common units, calorie and joule. Okay, calorie, you know what that is. If you go to like an energy drink, take a look at the label. Okay, so the energy that is associated, a certain amount of the energy drink is labeled on the bottle. Okay, most likely that's going to be calorie. And joule is another common energy unit in science, and 1 calorie equals to 4.184 joule. And sometimes you can hear kilocalorie. Of course, kilo means 10 to the third. So 1 kilocalorie means 1,000 calorie and 4,184 joule. And for electricity energy, we use kilowatts. Okay, and here these are the unit conversion factor between kilowatts and joule. All right, these are the energy units. Now let's take a look at this slide. Well, first question regarding energy apparently would be what is energy? Well, energy essentially is about the capacity to do work. And there are two types of energy, kinetic energy and potential energy. Kinetic energy is associated with motion. Okay, it's like you are driving your car with 70 miles per hour, so you have the car with the speed that is called the kinetic energy, the energy associated with the car movement. Okay, and apparently that's the higher the speed, the car would have higher kinetic energy. While in science, thermal energy usually is related to kinetic energy. Thermal energy is about temperature. Well, we know, let's see, chemistry. Okay, you have a bunch of molecules, and usually when you have higher temperature, the molecules will move faster. So when you have the molecules moving faster, then the kinetic energy of those molecules will be higher. Okay, so this is thermal energy. Now, potential energy is related to the position. Okay, it's like you are, on top of the Manning Hall, the 4th floor. Okay, you go from the 1st floor to the 4th floor, then you are getting higher position, then you are increasing the potential energy. Okay, in chemistry, chemical energy, those energy, the bond energy, for instance, that is associated with the positions of the electrons and the nuclei. Therefore, chemical energy is one type of potential energy. Now, what is the first law of thermodynamics? It means the total energy of the universe is constant. Another way to describe the first law of thermodynamics is the energy can be converted from one type to another type, but energy cannot be created from nowhere and it cannot be destroyed. Okay? How do we understand the conversion of energy from one type to another type? Well, here, these two pictures show us very good example. The first one is a waterfall. On the higher position, water molecules have higher potential energy, and when they go down to the bottom of the waterfall, potential energy of the water molecules get converted to kinetic energy. Okay, so it's the molecules will go faster and faster if you let them keep going. Now, another example is a roller coaster. Well, I don't know whether you tried the roller coaster or not, but essentially before you start rolling, you have to make sure that you go to the higher ground, right? You make sure that you have enough kinetic, you have enough potential energy, and then you let the whole train go, and then the potential energy will be converted to kinetic energy to go through those loops. Okay, so this is the first law of the thermodynamics. Now, let's talk about some important features of or properties of energy. Well, when we in science, when we talk about a system, okay, it's like a chemistry. You are talking about the reaction system. Now, when we talk about the energy that is associated with a system, we call it internal energy. And like we discussed before, usually energy, there are two types of energy, kinetic energy and potential energy. Therefore, when you consider the internal energy, you have to consider both kinetic energy and potential energy. Now, for those energy, doesn't matter kinetic energy or potential energy, there are state function. It means the value of the energy depends on the state of the system. Okay, what does that mean? Let's use this picture as an analogy to explain what the state function is. Well, here you can see the bottom of the mountain and the top of the mountain. The elevation of this mountain is 10,000 feet. Now, the elevation apparently is going to be a state function. Okay, so as long as you are moving from bottom of the mountain to the top of the mountain, the elevation is always 10,000 feet. It doesn't matter which routes you take to get to the top. Okay, so elevation stay as the same. Okay, it only related to the starting points and the end points. All right. Now, if you start from the middle of the mountain, let's see here, then the elevation apparently would be less. Okay, but again, it doesn't matter which route which path you are going to take. The distance, the travel distance, on the other hand, is not a state function, because if you take this route, then the distance would be shorter. If you take this route, apparently the distance would be longer. All right, so the distance is related to the path you are going to take. Therefore, distance is not a state function. Okay, so these are the some important properties of kinetic energy. Now, in science, as I mentioned a moment ago, we care about the energy that is associated with a system. Okay, with a system. And meanwhile, according to the first law of the thermodynamics, energy can be transferred, can be converted, right? So besides the energy that is associated with the system, we also care about the energy that is associated with the surrounding of the system. How do we understand a system and its surroundings? Well, let me give you one example in chemistry. Well, in chemistry, your project is to chemical reaction. Okay, you set up the flask, you add all of the starting material in the flask, and then the reaction mixture inside the flask would be your system, and the air around the flask would be surroundings. Okay, so that is how we discuss the reaction system and its surroundings. Okay, for this particular case, and the energy can be converted, can be transferred. So when you do a reaction, let's see again, reaction in a system. Okay, the energy can be transferred from a system to its surroundings. In this case, the energy of the system will decrease. Okay, so delta S system essentially equals to, let me write it here, delta E SYS equals to E SYS final. F represent the final state minus E system I. I represent initial. Okay, so delta means change. So delta E system equals to the system energy at the final state minus the energy of the system at the initial state. Okay, so and if system is losing energy, apparently the final state, the energy of the system at the final state would be less than the energy of the system at the initial state. Therefore, delta E system would be negative. But since the energy is transferring from the system to its surroundings, if system is losing energy, the surroundings will gain energy. Well, apparently then, in this case, the energy change of the surroundings would be positive. It gets more energy. All right, let's take a look at this particular reaction? Well, if you let carbon react with oxygen to generate carbon dioxide, well, if you treat this one reaction as a system, okay, then the energy will be released by this reaction to the air around the reaction flask. Okay, so for the reaction system itself, energy is going down. It's decreasing. That is why delta E is negative. Another situation is when you do some chemical reactions, sometimes the system will absorb energy from its surroundings. In other words, the energy will be transferred from surroundings to the system. In this case, the system will get more energy. Therefore, delta E system would be positive. It gets more energy. Now, surroundings, since it's losing energy, delta E surrounding would be negative. Okay, energy is decreasing for surroundings. And so again here, this picture described the opposite situation for the reaction. This time, on your right side, reaction is between carbon and oxygen. It generates carbon dioxide. But on this side, it's the decomposition of the carbon dioxide. It generates carbon and oxygen. In this case, the decomposition of the CO2 will absorb energy from its surroundings. Okay, so energy of the CO2 system will increase. Okay, so that's why the arrow is pointing from the bottom to top. All right, so it's positive. The energy change of the reaction system would be positive in this case. All right, this is the first topic of chapter 9. Let me know if you have any questions.